conformational isomerism. So let us see the stereoisomers which are formed due to rotation around C sigma bond is called as rotomers, and the phenomena is called as rotational isomerism, which is also called as conformational isomerism. Now, let us see these conformers are interconvertible at room temperature and hence cannot be separated out. That means one can be converted to another one. Like that, if anything is converting from one form to another form, generally they are said to be interconvertible isomers. One compound have infinitive number of conformers. Why infinitive number of conformers are possible? Why? Because when between carbon and carbon single bond is there, infinitive number of rotations are possible. Okay, but there is a condition, that is compound which contains at least 3 continuous sigma bonds will show this conformational isomerism. There should be at least 3 continuous alpha bond, that is sigma bond should present in the molecule. They only shows this conformational isomerism. Let us see some compounds. Here CH4 molecule, let us consider. In CH4 molecule, total number of sigma bonds 4 are present, but there is no continuous 3 sigma bonds. That's why conformational isomerism is not possible in the case of CH4 molecule. But coming to the ethane molecule, here continuous sigma bonds are present, 3 sigma bonds are present, so it shows conformational isomerism. Like that, water molecule, if you consider H2O, I'm taking, in H2O also there is no 3 continuous sigma bonds, it cannot show conformational isomerism. In the case of H2O2 it is possible, and in the case of propane is also it is possible because there is a continuous sigma bonds. Right, here also we have 3 bonds, it shows. Propane also shows. And coming to the N2H4, N2H4 methyl alcohol also contains continuous sigma bonds, that is 3 sigma bonds, it shows. But in the case of ethene molecule, they cannot show conformational isomerism even though there is what 3 sigma bonds are present. We know in double bond one bond is sigma bond, other bond is pi bond, but due to presence of double bond, so infinitive number of rotations are not possible. Rotation is restricted. Why? Because double bond may twist. It is not giving number of conformers. That's why it is not showing conformational isomerism. Right. So these are the conditions and examples which compounds will show rotational isomerism. Next, let us see, we have to see a molecule from 3D to 2D representation. So here we have 2 types of representations. One is Newman's representation, other one is Sahar's representation. Let us see Newman's representation. In Newman's representation, front carbon is represented with a dot like this, whereas back carbon is represented with the circle. That I am representing here. See once, with pink color I represented how to represent a carbon. So center one, this one is representing carbon. Around carbon there are hydrogens or any other groups may present. Okay, for example here I'll consider H is present. We are representing this molecule, that is methyl group, like this. And coming to the next one, back carbon is represented with circle, which is represented with what? Yellow color. Okay, around that there are hydrogens. We can represent hydrogens in this way. So simply a molecule can be represented in this form. Okay, here what are they? Hydrogen, hydrogen, hydrogen. And coming to this, here also hydrogen, hydrogen and hydrogen. So here pink represents, right, front carbon, whereas yellow color represents back side of the carbon on which 3 hydrogens are present. Coming to the Sahar's representation, here we are using the lines. So straight line, around that here 3 bonds, 3 are hydrogens. In this way or in this way we can represent. So these are the 2 representations. Okay, that is Newman's representation, second one is Sahas representation, which is also called as side view representation. Now, angle and strain also we have to know to study about the structure of the molecules and conformers. So let us see what is angle and what is a strain. Angle is nothing but bond angle, will say generally. So that is the angle between two bonds at a same atom is called as what? Bond angle. The angle between two bonds at same atom is called as bond angle. Generally bond angle we are representing like this. Coming to dihedral angle, the dihedral angle is angle between two bonds at adjacent atoms is called as what? Dihedral angle. Adjacent atoms means just now I represented front and back side molecules. So here this is nothing but what? I'll take front one with the help of pink color. Okay, front carbon is this, whereas back carbon is this, on which hydrogens are present, CH3 and CH3, that is C2H6 ethane molecule you can consider. On this also we have hydrogens. So this is nothing but C2H6 molecule, 2 carbons, 6 hydrogens. Now dihedral angle is nothing but the angle between the two adjacent atoms, that means this angle. So this is called as dihedral angle, DHA I'm writing. Okay, dihedral angle. Now strains also two types, that is steric strain and torsion strain. Steric strain is nothing but the strain between two atoms is called as steric strain, whereas torsional strain is nothing but that is the repulsions or the strains between electron of two bonds. Electron of two bonds is called torsional strain, and whereas the strain between two atoms is called as steric strain. These are the two strains. Strains is nothing but repulsions we can say. Okay, repulsion generally we are considering. Now let us see one example in a molecule. In a molecule that is which contains two carbon atoms, around carbon atoms 4 hydrogens, and X, Y, two different atoms are present. Okay, afterwards in place of X and Y we are going to take two hydrogens or two methyl groups we can take, butane also we can take, hexane also we can take, cyclohexane. Like this in place of XY we can change the atoms. Just try to understand what type of rotomers are possible, that is nothing but what rotational isomers are possible by rotating by 60 degrees. That try to understand with the help of this example. So here in this example, the bond between CC, this carbon and this carbon. Okay, so first one I'm writing C1, this is C2. So C1 here, that is represented with pink color, front carbon. C2 carbon is backside. Okay, now backside is represented with yellow we discussed, right? Pink is nothing but representing front carbon. Now let us see, on the first carbon there is X, so that I represented here. Okay, now if front and back is arranged like this, look at this, the first structure whatever it is there, in which H, that is X, Y both are they are present on the same plane, you can say. X is front side, back of that Y is present, just assume like that, and the remaining hydrogens are same, front back. Such type of arrangement is called as fully eclipsed arrangement, generally will call. What? Fully eclipsed arrangement we call. Now this fully eclipsed arrangement when rotated by 60 degrees, then what happens when it is rotated by 60 degrees? Only backside carbon we are rotating, front side carbon is not rotated, that is fixed. Only one carbon you have to rotate. So we are rotating backside carbon. So why when you rotate by 60 degrees, right, it is coming like that. Our backside carbon is rotated by 60 degrees. The position of H changes like this, so that you'll get the gauche form. Second is formed. Right, now see H, that is XY, these two atoms are at 60 degrees position. Right, so that conformer is called as gauche conformer. Like this, infinitive number of conformers are possible, I said, right? So again 60 degrees if you rotate, 60 degrees if you rotate, you are getting partial eclipsed. Partial eclipsed will say. Is it clear? So third one is partially eclipsed. Again by rotating 60 degrees, partially eclipsed can be converted to staggered or anti form of the conformer. Staggered or anti is nothing but here both x and y are opposite direction. The conformer in which x and y both are at 180 degrees are opposite to each other, that conformer is called as staggered. Okay, staggered will say. Next, by rotating 60 degrees again, this anti or staggered is giving partially eclipsed again. Now this partially eclipsed rotated by 60 degrees, we are getting gauche form. Again gauche is rotated by 60 degrees, we are getting again starting conformer, that is fully eclipsed conformer is formed. Like this, by rotating one of the carbon, infinitive number of conformers are possible. So here, except this is fully eclipsed and staggered, whatever the middle conformers are formed, all they are called as Q conformers. That is gauche, partially eclipsed. All these conformers together called as what? Skew conformers we can say. Okay, skew conformers will say. Now let us see here eclipsed conformer. If you take eclipsed, fully eclipsed conformer I am considering. In the fully eclipsed conformer, here SS, TS, P. SS is nothing but what? Steric strain. TS is nothing but torsional strain. P is potential energy, and stability of that conformer let us discuss. In the case of eclipsed, that is the first isomer, this one. Okay, I am erasing this. Right, now in this compound eclipsed conformer, you see this one is eclipsed. See here steric strain is maximum. Why steric strain is maximum? Why? Because the groups X and Y both are close to each other. Between that two groups steric strain is present. Right, steric strain is present. Whereas why steric strain is present? Because that atoms are close. When atoms bulk groups are close, between the bulk groups there is a repulsions, there is a strain is existing. Whereas coming to the torsional strain is also maximum between the two. We know what is meant by torsional strain. It is a repulsion between the electrons, we discussed, right? That is also maximum. Coming to the potential energy is also maximum, but stability is minimum. Repulsions are more, right? Stability is less, stability is minimum. Coming to the staggered conformer is nothing but the fourth conformer, this one. In the fourth conformer, steric strain is minimum. Why? Because both X and Y are opposite to each other. The distance between the two is maximum. Repulsions are less, right? Stability is more. That is the reason steric strain is minimum, we can say. Torsional strain is also minimum, potential energy also minimum, but stability is what? Maximum in the case of staggered. So this staggered and eclipsed conformers are very important. Between these two, whatever the conformers are possible, all that conformers are called as skew conformers will say. Now Energy order and all that, let us discuss. Energy, if you see, the energy of eclipsed is more compared to partially eclipsed, then gauche, then staggered. This is the order of energy. So energy is maximum for eclipsed, so stability becomes less. So down stability order is given. This is opposite to energy order. Eclipsed is less than partial eclipsed, which is less than gauche, which is less than staggered, or which is also called as anti-conformer. Here I have given skew form. What is meant by skew form? Skew form is nothing but there are that is what infinitive conformers between the eclipsed and staggered form. They are known as skew forms. That means partially eclipsed, gauche, all these together are called as skew conformers. Let us see conformers in the case of ethane, which is very important. Okay, that is conformers of ethane, because we have in the syllabus. So let us see how to write these conformers. Here ethane molecule, we know the formula of ethane. Ethane molecular formula is C2H6. So bond line structure is like this. This is first carbon, second carbon. Every carbon has 3 hydrogens. Now I'm writing first carbon is represented with the pink line, second carbon is represented with yellow color. Sorry, pink color, and second one is represented with the yellow color. Now first carbon is stable. We are not rotating it, but second carbon is rotated by how many degrees? 60 degrees. So initially the position of these hydrogens are same, front back. Okay na? Right. So such type of conformers are called as what? Eclipsed. When eclipsed conformer is rotated by 60 degrees, we are getting staggered conformer. Right? Staggered conformer. This staggered conformer again rotated by 60 degrees, then we are getting eclipsed conformer. Okay, we are getting what? Eclipsed conformer is formed. Same way again it is rotated by 60 degrees. We are getting what? Staggered, or which is also called as anti-conformer. Again by 60 degrees. Eclipsed on 60 degree rotation, staggered is formed. This staggered again we are giving the starting one, that is what? Eclipsed conformer. So like this. So here we have 6 major conformers are possible in the case of what? Ethane. Now let us see which conformers are eclipsed, staggered and anti-staggered. What is the energy? What is the stability order? As we discussed earlier, that is we discussed about what you call xy, 2 terms are taken. In place of xy, here we have taken both hydrogens, then it is giving ethane molecule. Right, see here in the case of first one, that is eclipsed, third is also eclipsed only, at the same time fifth is also eclipsed. Okay, so first carbon, third carbon, that is first compound, third one and fifth one, these are eclipsed conformers. The remaining, that is second, fourth, sixth, second and fourth and sixth, these are called as staggered. Okay, or they are also called as anti-conformers. Energy of these conformers, if you observe, eclipsed energy is more compared to staggered. Eclipsed energy is more compared to staggered. Is it here? Stability order, if you consider, reverse order. Eclipsed is less than the staggered conformer. So this is in the case of what? Ethane molecule. And here graphically also we can discuss this. So generally here potential energy versus dihedral angle graph is written. So then you are getting the graph like this. So here potential energy of eclipsed, that is energy of eclipsed, is more than the staggered we discussed. So that I represented here by taking 0 degrees, 60 degrees, 120 degrees, 180, 240, 300, 360 degrees versus potential energy. So this is the graph taken. Now conformational isomerism in the case of butane, let us discuss. So here conformers of n-butane. So butane formula is C4H10. We are writing the structure like this, and this is the bond line structure. Here the rotation is between C2 and C3 carbon. So this is the rotation between C2 and C3. By rotating that, we are getting different types of the conformers. First one, that is eclipsed. We know in the eclipsed, two CH3 groups are at same place. One is front side, other one is back side. When it is rotated by 60 degrees, eclipsed can be converted to Gauche form. That means CH3 goes here and hydrogen comes here and hydrogen is here, and this compound again rotated by 60 degrees centigrade, then we are getting partially eclipsed compound. That means CH3 is present here and hydrogen is here and another hydrogen is here. Again by 60 degrees rotation, then this CH3 position becomes exactly opposite to the front carbon containing CH3 group. That's why we are getting which compound? Staggered compound, or which is also called as anti-conformer. And this is rotated by 60 degrees. Then partially eclipsed is formed. That means CH3 is here, here hydrogen and here hydrogen, and on further 60 degree rotation the compound formed is Gauche. In the Gauche conformer, CH3 position is here, hydrogen, and here also hydrogen. Again by 60 degree the starting compound, that is eclipsed, is formed. Here energy is also mentioned, that is eclipsed 19 kilojoules, Gauche 3.8, partially eclipsed energy 16, whereas coming to the staggered, which is also called as what? Anti, it is 0 degree, that is 0 Kelvin per mole, that is the energies. So like this, these are the 6 conformers. So between eclipsed and staggered, whatever the conformers are there, they are called as skew conformers. That is Gauche, partially eclipsed, all together they called as skew conformers. Now among these conformers, what is the order of energy and stability? If you see here, energy of the eclipsed is maximum, that is 19 kilojoules, which is highest among Gauche, partially eclipsed and staggered conformer. So here we have the structure 3 and 5. If you observe, both are partially eclipsed. Okay, that is 3 and 5 partially eclipsed, whose energy is same. And 2 and 6 if we consider, that is Gauche conformers, their energy is also same, that is equals to 3.8 kilojoules per mole. And the fourth one, that is staggered, is least 0 kilojoule per mole is considered. So the energy order becomes 1 is greater than 3 and 5, because 3 and 5 both are same partially eclipsed, they are having same energy, which is greater than 2, 6, which is greater than 4th, right? So first one is called eclipsed, and the third, fifth is called partially eclipsed, Gauche, and staggered is the order. Stability is reversed to this. Energy, stability, both are inversely proportional. Then the order becomes that is opposite. Now graph, if you observe here in the graph, energy versus dihedral angle if you take, right? So these are the graphs. We know that in the eclipsed, energy is 19 kilojoules, which is highest. Eclipsed is highest. After eclipsed, Gauche conformer, then partially eclipsed, staggered, partially eclipsed, Gauche, that I represented with the letters G, P, and all this. So this is the graph. Here very important point is, when attractive forces are present between the groups, like what type of attractions? Hydrogen bond, electrostatic force of attraction, then Gauche conformer is more stable than the staggered, right? This is the stability order. In general, stability. In general, staggered is more stable than the Gauche. Why staggered is more stable? Why? Because, see once here, staggered is more stable, right? Fourth conform is more stable, we discussed, right? This is the order. Here, two identical groups CH3, CH3 are opposite to each other. There is less steric hindrance, right? Angle strain is less, stability is more. Simply you can say that, right? The staggered form is more stable than the Gauche form. But when attractions are existing between the groups, then Gauche becomes more stable than the staggered. So let us see what type of attractions, how to represent that. I am taking one molecule here, that is a compound which contains OH and F. Between H and F, hydrogen bond is present, right? We know hydrogen bond is nothing but the bond between more electronegative atom and electropositive hydrogen is called as hydrogen bond. In the Gauche, this conformer is called as Gauche conformer because of hydrogen bond. Because of hydrogen bond, what happens? The stability increases in the case of Gauche compared to staggered form. Why? In the staggered, OH and F both are away from each other. There is no chance for the bond formation. But in the Gauche, they are just at 60 degrees only, and side by side you can say they can form hydrogen bond. Right? They can form hydrogen bond. That is the reason stability of Gauche increases than the staggered. And one more is what? Electrostatic forces also affect the stability we discussed. Here in the molecule, this one I am taking. So here what NH3 plus and COO minus, if we consider, between the positively charged and negatively charged ions, electrostatic forces are generally present. Okay, so this is electrostatic forces, and here this we call it as what? Hydrogen bonding. Due to hydrogen bond, due to electrostatic forces, what happens? Gauche conformer becomes more stable than the staggered conformer. So this is Gauche, whereas this is staggered. In general, staggered is greater than Gauche, but due to these special properties, that is hydrogen bond and electrostatic forces, not only this, even inductive effect also we can consider. When these are present, inductive effect also you can add. The third one is inductive effect also. Inductive effect also we can add. That I'll show you in this compound. So here I have a compound that is CH3. So CH3 is having partially what you call positive charge. Cl is having partially negative charge. So between these two, there is a inductive effect. Inductive effect is an electronic effect that we are going to discuss soon. Inductive effect, which is also affecting the stability, right? So because of this inductive effect, what happens? Gauche becomes more stable than staggered. So this is staggered, right? So in the staggered, there should be what? Cl is present here, Cl. So this is the staggered conformer, this is the Gauche conformer. So these three are special conditions why Gauche is more stable than staggered. Next, coming to one more compound which is very important. This is also important point. Look at this example. Here the compound 1, 2, if we consider ethane, name of the compound is what? Ethane 1, 2 dicarboxylic acid. Ethane 1, 2 dicarboxylic acid. So in the case of base and acid, we are going to discuss what type of products are formed in this. Now when pH is greater than 7, the solution becomes basic, right? Basic, and here if we observe the compound which are formed, see, basic substance in the presence of base, COO minus, COO minus, bases generally nucleophiles we can say, right? That is minus charge is there. And here both COO minus, COO minus, there is a repulsions between the carboxylate ions. Because of repulsion, stability decreases. So this is less stable than the which compound? Staggered compound, in which COO minus both are away from each other, then stability is more. But here COO minus and COO minus both are side by side, both negative charges, so repulsions are existing between that. Because of that, stability decreases in the case of Gauche conformer. When pH is less than 7, the solution becomes acidic here. Okay, the solution becomes acidic. So when solution becomes acidic, what happens? Look at this structure, that is Gauche conformer, and this is staggered. Now you know staggered Gauche difference, right? Right. Because of existing of hydrogen bond between keto group of 1 carboxylic acid and H, that is OH group of the another COH group, stability of Gauche increases, then staggered form. This is the reason. This is in the case of what? 1, 2 dicarboxylic acid of ethane molecule. Next, conformers of cyclohexane. So here cyclohexane, it is a cyclic form, 6 carbons are present. In open chain alkanes, generally carbon shows sp3 hybridization. When hybridization is sp3, bond angle is 109 degrees 28 minutes. Okay, there is no distortion in the bond angles. Okay, when hybridization is sp3 and alkanes, that is we are taking, that's why there is no distortion. But in cycloalkanes are different from open chain alkanes. Now in the cycloalkanes, like cyclopropane, if you consider, so this is called as cyclopropane. In cyclopropane, bond angle is 60, right? Then angle strain becomes, we know 109 degrees 28 minus 60, if you substitute, you are getting 49 degrees 28 minus. This is the what angle strain means. There is an angle strain in the case of cyclopropane, and the same way cyclobutane and cyclopentane. In all these compounds, there is a angle strain, right? When there is an angle strain, generally they are not showing conformational isomers. Isomerism is not possible. What type of isomerism? Conformational isomerism is not possible in the case of compounds which shows angle strain. But coming to cyclohexane, right, bond angle is 120 degrees. In this, there is no angular strain and it shows conformational isomers. In this, we have different types of isomers, that is cyclohexane forms generally 4 types of isomers. In that, which one is more stable, which one is less stable, which is having more energy, let us discuss. So this cyclohexane shows chair form. Total number of carbons how many? 1, 2, 3, 4, 5, 6. So cyclohexane I am representing in the form of chair, and this is both 1, 2, 3, 4, 5, 6. This is not carbon. Okay, so observe carefully. Right. Next, boat form. So chair form, this is twist boat form, and the third one is boat form. Here also 1, 2, 3, 4, 5, 6, cyclic form only. And the fourth one is half chair form. 1, 2, 3, 4, 5, 6. 6 carbons. So these are the four possible conformers of cyclohexane. Among these conformers, energy order, if you see, chair conformer is having what you call least energy when you compare with half chair form. Okay, half chair form. So this is the order of energy. Chair form energy is less than twist boat form, then boat form, then half chair form. Right? Then energy is less. Energy is less. Then stability is what? Energy stability order we already discussed. Right? Stability is more, then energy is less. Inversely proportional. So stability order becomes chair form is more stable, energy is less, then twist boat form, then boat form, then a half chair form. Okay, so here I have given numbers for chair, twist boat, boat and half chair that I represented graphically in this way. So energy, okay, which one is having least energy? Least energy is there for chair form, that is for first. Okay, then after that second is given to twist boat, right? Third one is what? Boat form. Then fourth one is half chair form. Next, so same thing I have given here also. Free energy versus rotation. If you plot a graph, chair form is having what? Least energy. Half chair form is having highest energy, the least energy. In any way we can represent chair form. Okay, and this is the boat form. So here cyclohexane with methyl group, which group? Methyl group, in the equatorial position is more stable than axial position. So here whatever the CH3 group is there, that CH3 group is at equatorial position. When it is in equatorial position, which is more stable, that is 95% it is stable when compared with axial position. CH3 with axial, it is just 5%. So related to this, more sums we are going to solve. So that afterwards we'll discuss. Thank you.